The last of the heat videos deals with the idea of heat capacity. That's the letter C on the back of the reference table. Heat capacity is how much heat it takes to increase the temperature of an object exactly 1 degree Celsius. It depends on two things: the mass of whatever we're looking at. So for example, if we're looking at a body of water, how much water are we looking at? And the chemical composition of what makes up the substance. If you have more mass, you're going to have a greater heat capacity. So when we talk about mass, for example, if you have a tea kettle at home and you have to heat that up, you could boil the water pretty quickly. It may only take a few minutes. But you know, when you open your swimming pool in the summer, it takes a really long time for it to get to a nice, comfortable temperature, unless, of course, you have a heater. But it takes longer to heat up a larger mass of water, like a pool, than it would to heat up a small tea kettle. So the pool contains more molecules and has a larger heat capacity because it has a greater mass. So different substances, we also said heat capacity depends on chemical composition, will have different heat capacities. So for example, metals have really low specific heats because they heat up really, really quick. Water has a really high specific heat because it takes a long, long time to heat it up. So when we're talking about water, we could use, there's a value on the front of the reference table, 4.18, that will indicate what the specific heat of that substance is. If we're using something else besides water, since every object has a different chemical composition, they're going to have different specific heat values. But you've observed the effects of specific heat for sure. If you've ever, in the summertime, touched a metal swing set, for example, you notice that the metal gets really, really hot really quickly. The metal, you could have a metal swing set and a wood swing set, the metal would appear hotter. So that's due to the difference in specific heat, how much heat it takes to raise the temperature 1 gram of the substance 1 degree Celsius. So here's our equation that we're going to use. Anytime we're looking at specific heat, the C value is specific heat. And it tells you that on the reference table. Again, you don't have to memorize it. Delta T is the final temperature minus the initial temperature. It doesn't matter if it's in Kelvin or Celsius since we're just looking at a difference, right? So you can convert them both, but we're just looking at the difference when we calculate delta T. So don't worry about that. And again, looking at our heating and cooling curve, we've talked about when you're on this lower plateau, we're going to use Q equals MHF. When we're on the higher plateau, we're going to use Q equals MHB. Well, guess what? When we're in between, meaning our temperature is changing, the delta T, we're going to use the equation Q equals MC triangle T, because the triangle T means a change in temperature. My temperature is changing from here to here. Again, here to here, my temperature is changing. So on this part of the curve, you would use Q equals MC triangle T. So any point where the temperature is increasing, so where we have inclines here, here, and here, we're going to use that Q equals MC delta T. Q equals MC triangle T, or delta T. Doesn't really matter as long as you understand that delta T means a change in temperature. We're also going to use the corresponding parts on our cooling curve. So here, at all those points, we would use the Q equals MC triangle T. Anytime the temperature is going to change. Because remember on the bottom here, this first plateau is Q equals MHF, and this top one was Q equals MHB. It's important that you know when to use each equation because we're looking at each one separately, but on a Regents question, you're going to have to identify which one to use. Okay, so let's look at our first specific heat calculation. How many joules? Annotate. Joules means heater energy. That's a unit for, we could say. Heater energy are absorbed. Absorbed means endothermic. When 50 grams, grams represents the mass of water, awesome, we could use table B, are heated from 30.2 degrees Celsius to 58.6 degrees Celsius. Again, remember we don't have to change those to Kelvin because we're just looking at a temperature difference. So let's set up our equation. We have Q equals MC delta T. Let's plug in what we know. We're looking for the joules, so our Q is our X, right? The mass we wrote down is 50 grams. C is the specific heat capacity of water. That's on the front of your reference table. It's 4.18 joules per gram Kelvin. Like I said, it's not going to really matter, though, the unit, as long as we're finding the difference in temperature. And the last part is delta T. Let's just go over how you find delta T. Delta T is equal to the final temperature minus the initial temperature. You need to know what that represents. It's not listed on your reference table. I would write it in now as we practice, but by the time it comes to the exam, you need to know what that is. Final temperature minus initial temperature. So that would be 58.6 minus 30.2. So the value we get for delta T is 28.4. So plug that in there, 28.4. The difference would be in Kelvin or Celsius. It's still a difference. Kelvins cancel out, grams cancel out, and we're left with joules. And we get an answer of 59,356 joules when we just multiply those all across in our calculator. Next problem. The temperature of a sample of water in liquid phase is raised 30 degrees Celsius. Okay, so let's set up our equation. We have Q equals MC triangle T. A couple things that we need to keep in mind. They want to know what's the mass, so mass is going to be our X. Okay, so let's plug in what we know. I'm sorry these answers are here, just ignore those. I couldn't get them off after we started the video. So the Q value is in joules. We're going to plug that into our Q spot. So we have 3762 joules equals the mass. We already identified that's our X. The C is specific heat. We're talking about water, so we could use the value from table B, 4.18. And delta T, they didn't give you two temperatures, and that's usually the best way to know that we have to use delta T, but they tell you the temperature was raised by 30 degrees Celsius. So we're going to plug that in as our change in temperature. Because remember, on our heating curve, if we were talking about Q equals MHF or Q equals MHV, the temperature would not change. It would be staying constant, because temperature stays constant during a phase change. So solving for M, we would get that M is equal to 30 grams. Okay, last one. Calculate the heat energy for Q equals MC. Alright, the temperature of a piece of copper. Okay, something to keep in mind, we can't use table B because this is not water. Can't use table B. With a mass of 95.4 grams, increases from 25 degrees Celsius to 48 degrees Celsius. When the metal absorbs, remember absorbing is that okay, right? 849 joules. Joules is the heat. What is the specific heat? That's the C of the copper. So we're solving for a specific heat because it's not given to you in the problem. That's what we're trying to find as the C. So we have Q equals MC triangle T. The heat value that they gave us is 849. Let's plug that in. Equals the mass. The mass is 95.4 grams, coming from here. C is what we're trying to find. And delta T, remember, is temperature final minus temperature initial. We get a value at the end that the specific heat is equal to 0.3869 joules per gram degree Celsius.